first day. I didn't record the first day. And the recordings are posted on the YouTube channel. So I did upload the recordings on the YouTube channel as well. So if you subscribe to that, you have all of these. So describe what it means geometrically, graphically, what to take the inverse of a relation. If I give you a graph, what do you do to that graph to get its inverse, the graph of the inverse? Can somebody tell me?
You switch out the x and y values.
Okay, so that is more along the lines of number 2. Describe the relationship between the domain and the range, the x and the y values. So let's go ahead and answer number 2, Eric, with your answer, right? So what you're doing is you are interchanging the x and the y values to get the inverse. So the domain of the original function becomes the range of the inverse. The range of the original function or relation becomes the domain of its inverse. So that's more what I was looking for number 2. But Eric, you're on the right track. So if you are interchanging your x and your y values, let me give you a little hint. So let's say I have a graph. So here is my parent. Let's just say I have a parent here, f of x, and this one is a function, but I don't have to give you a function. If I ask you to take the inverse, what are you doing? What does it mean to take the inverse? What did we do? We did an activity yesterday with patty paper. With folding pad of paper, what did we do?
You reflect across y equals x.
Abiela, you are absolutely correct. You reflect the original graph across the line y equal x. So if we had this line y equal x, the inverse, actually, let me do that in a different color, right, is the reflection across y equal x. Good. Okay, so algebraically, so we talked about it geometrically, we talked about it with respect to the domain and the range, the x and the y values. Let's go ahead and see what happens if I were to give you an equation. You should be able to determine if it is a function, the original. So this is our original one. Actually, let me do that in blue. This is our original. So everything that we answer here is going to be pertaining to the original equation I give you. Then you are going to find the inverse of that algebraically and tell me about the inverse. Okay? So the original equation is what type of equation? How would you describe that? What is this? What does the graph of that look like?
Linear.
It is linear. It is a line. So and is it a function? Is the graph of y equal 3x plus 2 a function? Yes, you are correct. Yes, it is. So is the original relation y equals 3x plus 2, the original, is it a function? Yes. Now, what is the underlying parent function? If I strip away all transformations, can you tell me what the underlying parent function would be? This is a little tricky. So if I'm looking at this, if I take away the transformations, that plus 2 is a transformation and the times 3 is a transformation, what is left? What is the underlying parent? Does anybody know?
Y equals x.
Beautiful. Y equal x. Excellent. Now, in looking at y equal x and looking at this, can you describe transformations? What are we changing in the original function? Can you describe transformations? What does the plus 2 do? Any idea what that plus 2 does to the parent?
Shift horizontal to the left by 2 units.
Well, if I were impacting the x, if it were y equals 3x minus or x plus 2, then I would be shifting, right? If I impact the x, that is a horizontal shift. But this is plus 2 is on the outside. It's not directly connected to the x. So what transformation is that?
Shift up by 2 units.
Yeah, it's a shift up 2. And then if I were to address this 3, that would be changing my slope, right? That would make it steeper. So that would be a vertical stretch by a factor of 3. Vertical stretch by factor of 3. Now, if I were to graph this y equals 3x plus 2, I know it has a y-intercept of 0, 2 because of that. From there, I could go up 3 and over 1, and I could graph this, right? I could graph my original function. That's the graph of y equals 3x plus 2. You can check it on Desmos. Now, what is the domain of that original function? What is the domain of that line? Can you tell me?
Negative infinity to infinity.
Yes, it is all real numbers. And what about the range?
Negative infinity to infinity.
Beautiful. Okay, so we have now talked about this original function. We said it was a function. We described the transformations made to the underlying parent function, and we stated the domain and the range. Now, to take the inverse of this, you said I'm changing my domain and my range. I'm reflecting it across y equal x. So algebraically, if I'm interchanging my domain and range, can't I take this equation and to easily find the equation of the inverse of the given function, I could interchange my x and my y. So to find the inverse, I'm going to let y equal x, I'm interchanging them, equals 3 times, now that x becomes y. So do you see how I've just interchanged the x and the y? That's all I've done. I've interchanged literally the x values and the y values. That's what it means to take the inverse of a function. Interchange the domain and the range. So now if I have this, I can just solve for y. So if I'm solving for y, what would I do? What would I do next? Can you tell me? If I'm solving for y.
Subtract 2 on both sides.
Okay. All right, then that would give me, that is correct, x minus 2 equals 3y. And then my last step to solve for y would be what? How do I isolate the y? What's standing in the way?
Divide 3.
I'm going to divide everything by 3. Okay, so what does that give me? That gives me, and it doesn't matter what I put on what side of the equation because the two sides are equal. So that would be y equals x over 3 minus 2 over 3. And if I really want to see the slope as the coefficient of x, I could write it like that. So I now have the inverse of the given function. Do you see how I arrived at that equation? Those are inverses. And I could graph that. If I came back to my original Cartesian plane, I could plot that 0, negative 2/3, I could go up 1 and over 3. And guess what? That would be the reflection across y equal x. Do you see that? That's cool. That's cool. All right. So let's talk a little bit more about this equation and the graph of this reflected function. Looking at the inverse. So now I'm looking at this and I'm looking at this. And you should know that if I wanted to write it using function notation, it would be let me write that a little bit bigger. F inverse of x. Have y'all seen this notation before? Yes? Inverse function? Okay. Now, looking at this inverse, this graph here, is it a function? Is the inverse a function? We said the original graph in blue was a function, but is the inverse in green also a function?
Yes, it's a function.
Yes, it is. It is. Unless it's a vertical line, all lines are functions. Now, what is the underlying parent function for that inverse? Y equal x. That is correct. Now, what transformations am I making to this parent to get this image function here? I've done a shift and a compression, right? Can you describe those? For example, what does that do to our parent? Eric, Abiella, Christopher, anybody?
It is shifted down by 2/3.
Yes, it's shifted down 2/3. And what about this? What does that do?
Vertical compression by a factor of 1/3.
Yes. Exactly. And what is the domain of the inverse of the original? What is the domain of the green one, of the green line, the graph?
Negative infinity to infinity.
And what about the range?
Negative infinity to infinity.
Beautiful. Okay, so that's a nice linear one. So I can now say, let me write that a little bit better. I have the original function and I have its inverse, and I've identified some information. Now this one's simple, it's a line. They get a little bit more interesting. So we're going to do the same process, but now we're going to do it with a different type of function. So let's take a look at the next type of function. So maybe let's first start off talking about what type of equation is that? Do you recognize it? Can anybody tell me what type of equation that is?
Quadratic.
It is quadratic. I could technically, if you don't really see it, you could rewrite this, since this binomial x minus 6 is squared, I could multiply it by itself. And I could get this equation, and that would make it abundantly clear that this is quadratic, right? But I want to work with this form because I think this is an easier form to work with respect to what we're doing. These are equivalent, right? All I did was FOIL. Yeah. Okay. So there are two different forms of this quadratic equation, but if you can't really see the highest exponent of x is 2, maybe expand it. Okay. So now let's focus a little bit more. I have my original relation. You said it was representative of a quadratic function. So is it a function? Yes, it is. Can you tell me the underlying parent function to this given function? What is the underlying parent? Eric? Nathan? Anybody? I'm
Y
sorry.
equals x squared plus x.
Just y equals x squared, right? Just plain old y equal x squared. That is your underlying parent. So I could plot points if I really wanted to. 1, 2, 3, 4. There's my parent. Y equals x squared, right? Parent quadratic function. That is the underlying parent function to this one. Now, describe the transformation made to this parent to get that image, to get this resulting function. What did we do? Describe the transformation. So in other words, this -6. What did that -6 do to the parent? Y'all gotta know your transformations. Nathan, do you know your transformations? Christopher, do you know your transformations? I'm not. Christopher, you know it? What did this -6 do to this parent? Any ideas? Eric, any ideas?
Horizontal shift to the right by 6 units.
It is a horizontal shift to the right, 6 units. You guys, if you don't understand this, ask me. These transformations are very important. So that -6 attached to the x is telling us to shift it to the right. So if I shift it to the right 6, 1, 2, 3, 4, 5, 6, this goes here, right? So my image function looks like this. This is the parent. This is the image. This is this. Okay? What is the domain of this function? What is the domain of that function, of this function here? What is the domain? I'm looking at this graph here. What is the domain? Can you tell me?
All real numbers.
It is all real numbers. The domain is all real numbers. Can you tell me what the range is? The range.
Zero to infinity.
And including 0. That is absolutely correct. That is correct. That is absolutely correct. Okay, so now we have described the original relation. Let's talk about its inverse. So in other words, if I'm taking this here, and I'm reflecting that across y equal x, the question is, what does the inverse look like? We know it's a reflection across y equal x, but let's talk a little bit more about it. Let's take the equation and let's find the inverse. So remind me again how I can do that really easily. How can I find the equation of the inverse? Quick, easy way.
Switch the x and y.
Switch the x and the y. So now this becomes x equals y minus 6 quantity squared. Now, I'm solving for y. What might I do next? Do we know algebraically what we would do? Eric, you're not really saying anything.
Square root it.
Square root each side, yes. That is absolutely correct. Okay, so that's going to give me y minus 6 on the left, and that's going to give me plus or minus the square root of x, sorry, on the left. Do you see how I simplified? The square root of something squared just becomes what is being squared. Now, the last step in solving for y would be what? Still need to isolate the y. Add 6 to both sides. Now, at this point, there's a couple of ways we can write it. We can say y equals 6 plus or minus the square root of x, or if you prefer, y equals plus or minus the square root of x plus 6. I personally like this one because it's easier to identify the parent and the transformations, but these are equivalent. So I now have the inverse function. Oops. There is my inverse. Let's talk a little bit more about that. First of all, do you know automatically if this is a function? Is this inverse a function? Do we remember from where we built our library of parent functions? Do you know what the square root function looks like? Y'all have it, right? We did it. What does the graph of the square root function look like? Well, I kind of just told you it was a function. Y'all should be able to recognize these parents, right? That's the square, y equals the square root of x. That's your square root function. So if I look at this inverse and I ask you, is it a function? Is it? Yes, no? Uh-oh, where did my stuff go? Do you see my stuff?
No.
It went away. Oh, no. It just logged off. Nobody says anything. Join. Kicked me off. I kicked myself off. Okay. Let me share. Am I back? No. It's still not sharing. Who? Well, it says I'm sharing. Oh, I am sharing. There we go. We're back. Okay, as I was saying, this is the graph of the parent square root function. So if I took this and I reflect it across y equal x, we expect to see something that looks like that, right? Not oriented at the origin. So what would be the inverse? Well, we've found the inverse. This is the inverse. Is it a function? Knowing that it looks like this, is it a function? Yes or no?
Yes.
It is? If I draw a vertical line there, I'm passing through it twice, right?
You're right.
So it's not a function. So no. The inverse is not a function. Now, looking at this inverse, what is the underlying parent to that inverse? If I strip away transformations, what would be the parent? Do we know? I know this is pretty heavy duty, but you know, this is algebra 2. You should have already seen this.
Y equals square root of x.
Beautiful. Thank you, Eric. Thank you. Y equals the square root of x is the underlying parent. Now, what have I done to this parent to get this image? Describe the transformations. So, for example, what does this plus 6 do?
A vertical shift up. by
Yes.
6 units.
It's a vertical shift, and I'm just going to abbreviate and go up 6. Okay, now there is another transformation, right? If we know that the parent is this, but the entire inverse is this, what is this minus sign in front? What type of transformation is that to the parent? A minus sign in front of the x tells us to do what?
Reflection across the x-axis.
It is a reflection across the x. Beautiful. And that's what gives us this. Now, looking at that new one, now remember, we have shifted it up 6 as well. So, oops, I better erase. There's our parent. We shifted it up 6. And then we also, in addition to it, included the reflection, right? So our graph is up here. Can you tell me the domain? I'm looking for the domain of this function. What is the domain? What is the domain? Can anybody tell me?
0 to infinity.
Including 0. Yes. And what is the range?
Negative infinity to infinity.
Absolutely correct. And do you see that the domain of the original relation is the inverse? This is range. And vice versa, the range of the original function is the domain of its inverse. Do you see that? So you really don't even have to calculate it. If you know about the original function and you understand the relationship among the domain and range of the original and the inverse, you don't have to calculate anything. Okay? So let me just, for completeness, state the inverse that we found. Okay? That's the inverse of this parent. All right, I want you to try the next one. It's very similar to the one we just did. I want you to take the original parent, so here's my parent, and I want you to find the inverse, and I want you to populate this table. This should not take that long. So let's go ahead and do this one. It's very similar to the one we just did. So go ahead and work on that. If you have questions, ask me, ask a math friend in the class, whatever makes you happy. When you think you got it, raise your hand in teams. When you think you got it. When you think you got it, let me know. Nathan. So we're working on this example here based on what we did in the previous example. Okay, Eric thinks he's gotten it. When you think you've been able to find the answer, the inverse, and answer and populate the table, raise your hand in teams. Or if you need help, let us know. Let us know. Don't just sit there floundering. So we're looking at the original relation, determining is it a function, what is the underlying parent, describe the transformations made to the parent to get this one, state the domain and range of this original relation. Then we're finding the inverse, interchanging the domain and range, we're finding the inverse and answering the same questions. Natalie thinks she's gotten them. Okay, great. Give it another minute or two, and then we'll go over it and see if we understand. Okay, one more minute and then we'll go over it. Ariana. Oh, Abiella. I think she's gotten it. Okay. All right. So if I am looking at this equation here, first tell me what type of function that, or sorry, what type of relation is that? How would you describe y equal x squared minus 4? Anybody? What type of equation is that? Abiella, you look like it's, yes, it is quadratic because the highest exponent of x is 2. So it is a quadratic equation. My question to you, is that original equation a function? Is that a function? Is this a function? Oh, heavens. Is that a function?
Yeah.
Yes, it is. The graph of this is a parabola, but what is the underlying parent function? What is the underlying parent function? Strip away the transformations. What's the underlying parent function?
Y equals x squared.
Beautiful. Y equals x squared. So that is the underlying parent. Now, if I think about the parent, here's my parent, right? What am I doing to the parent to get this graph? What transformation is being made? What is this minus 4 doing to the parent?
Vertical shift down.
It is a vertical shift down 4. So there's our new equation, which is really this graph. Okay, so it is a vertical shift down 4. Now, looking at this graph, what is the domain of that graph? Domain.
Are real numbers.
It is all real numbers. What is the range for this blue function? The graph of that quadratic function. What is the range?
-4 to infinity.
Including -4. Yes, negative and 4 to infinity, because it includes that point. Now, let's talk about the inverse. Let's talk about what happens when we reflect this across y equal x. To do that, we said that we interchanged the x and the y. That's all we did. And then we solved for y. So if I'm solving for y, I would add 4 to each side, giving me y squared equals x plus 4. And then what would I do? To solve for y. What would I do?
Square root them.
I'm sorry?
Square root.
Yes, you would square root each side. So then y would equal plus or minus the square root of x plus 4. So what is the equation of the inverse? Plus or minus the square root of x plus 4. So while our original was x squared minus 4, our inverse was plus or minus the square root of x plus 4. Now, is the graph of this a function? Well, if you have trouble identifying that, let's think about what the underlying parent function would be. If I'm looking at this, what would the underlying parent function be? Y equals what?
X squared.
The square root of x. The square root of x, right? If I'm looking at this, the underlying parent is y equals, the square root of x. That's the underlying parent. So the underlying parent looks like this. But what have I done to it? I've added 4 to the x, and then I've also incorporated this minus sign, right? So what does that plus 4 do? What does the plus 4 inside the radical attached to the x do to the graph of my parent? Abiela, I see your lips moving.
No, it's just I kind of messed up when I was doing it.
Oh, that's okay. That's okay. Can anybody tell me what is that plus 4 inside the radical attached to the x do to the graph of the underlying parent function?
Horizontal shift to the left.
Horizontal shift to the left. 4, right? So now I'm here. Okay, now what does this minus sign do?
It reflects across the x-axis.
It's a reflection across what? The x-axis. So now I'm looking at this, right? That is the graph of my inverse. That entire thing. So tell me, and you really don't have to do any work if you understand the relationship between the original and the inverse, what is the domain of this function? I mean, of this relation. What is the domain?
Including -4 to infinity.
-4 to infinity. And I know that because it's the range of the original. And what is the domain of this inverse relation?
All real numbers.
It is all real numbers. And again, I know that because it is the domain of the original relation. Now, is the graph of this inverse a function? No, it is not. It does not pass the vertical line test. Okay, now you should be able to take any equation. Well, I say many equations. You should be able to recognize the underlying parent, determine if it's a function, state, domain, and range, apply transformations, take the inverse, and answer questions about the inverse. Okay? So that was the point of all of this. So hopefully this is making it a little bit more clear as to really understanding transformations in addition to taking the inverse of a function. Any questions on this? This is super important. Okay, now what I want to do is return to the packet, and I want to look at what happens when we now take the inverse of an exponential function. In particular, if I look at this function here, what type of function is that? How would you describe that function by its graph? We did this. What does this represent? What type of function? Abiela, are you saying something?
Was it called like cubic?
I'm sorry?
Like, wasn't it like I don't know.
We did the paper folding, right? And we found a constant ratio. We wrote the equation as a hint in this form, right? Where B is the constant ratio. If we have a constant ratio, what type of function is that? Nathan, do you know?
Linear?
No, it is not linear. This is not the equation of a line, my dear.
Oh, sorry.
What
Quadratic.
type? Not quadratic, because, so again, linear in slope-intercept form is this. Quadratic was this. What was this equation representative of? Anybody? Eric? What type of function was that? Go back and look in your notes. I'm not going to tell you. We did this. We did this right after we did the paper folding. Go look in your note packet. You tell me. I'm not saying anything until you tell me what type of function that is that has a constant ratio. Remember that table, those tables I gave you, the sheet of tables, and I asked you, is it linear, quadratic, or what?
Exponential.
Exponential, Natalie, thank you. Exponential. This is the equation for an exponential function, right? And if b was greater than 1, we called this what type of exponential function? If the base b, the constant ratio, was a number greater than 1, what type of exponential function was that? Look in your notes. I don't see y'all looking in your notes. Look back in your notes and you tell me, for an exponential function,
A growth.
yes, it is. Thank you. Exponential functions had a constant ratio, meaning if you divide, right, you got a constant ratio, quotient, division. So y2 divided by y1, if we did the division, we got a constant ratio, constant multiple, so to speak. That was represented in our equation with b. If b was greater than 1, it was growth, which is what is demonstrated here. If b was between 0 and 1, a fraction, it was decay, right? And it looked like that. Y'all got to know this. Oh my gosh, this is going to kill you in pre-cal. All right. So if I take the inverse of an exponential growth function in particular, but really any exponential function, if I take the inverse, if I reflect this exponential growth function that you see here across this line, you are going to get this function. This function is known as a logarithmic function. Okay? So geometrically, a logarithmic function is just the inverse of an exponential function. It's just an exponential function that has been reflected across y equal x. So what are you doing to get the equation of a logarithmic function from an exponential function? You're just interchanging the x and the y, and you're solving for y. That's it. So logarithmic functions aren't these weird, mysterious, difficult things. Yes, they have rules, but logarithms are just exponents. They're reflections of exponential functions. So if I think back to my exponential function, so for my exponential function, my domain was all real numbers. My range was 0 to infinity. Remember, because we had a horizontal asymptote here. So that's why my range was 0 to infinity and didn't include 0. So if I take that exponential function, knowing what I know about inverses, and I reflect that exponential function across y equal x, can you tell me what the domain of this logarithmic function is, the parent logarithmic function? Can you tell me what the domain is? We said that this is just the inverse of an exponential function. So we know the relationship now between the domain and range of a function and its inverse. Right? Didn't we just talk about that? So what is the domain? Well, look at the graph. What is the domain of this logarithmic function? Okay, Eric, you told me that the relationship between the domain, between a relation and its inverse is that the x and the y change. The domain and the range change. So if this is the domain and range for the exponential function, and a logarithmic function is its inverse, you should be able to tell me the domain and the range of the inverse of this function.
0 to infinity.
0 to infinity, right. And then the range would be all real numbers. The domain of this function is the range of its inverse. The range of this function is the domain of its inverse. And if an exponential function is the inverse of a logarithmic function, you should be able to tell me that. So knowing that, if this is a horizontal asymptote for an exponential function, what does this become with respect to the logarithmic function? Can you tell me that? If an exponential function has a horizontal asymptote, how does that represented in a logarithmic function?
Becomes a vertical asymptote.
Thank you very much. It becomes the vertical asymptote. Do you see that? Because we know based on that investigation we did, if you take a horizontal line and you reflect it across y equal x, it becomes a vertical line. So that horizontal asymptote for an exponential function becomes a vertical asymptote in the logarithmic function. So that means if you have a logarithmic function, you cannot ever have an input to a logarithmic function that is negative. Okay? So let's go ahead and make sure that we understand. But before we do that, actually, do I want to, let's see. Yeah, let's go ahead and do this. I wanted to move on to polynomial functions, but let's go ahead and do this. All right, so this is an exponential function. This is an exponential growth function where the base is 2, so I know it's growth. So I can substitute in values for x. I can choose negative values. I can choose positive values. It doesn't matter. Actually, let me go ahead and write that in here. I could choose -2, -1, 0, 1, and 2. If I substitute in -2 for x, what is y here? If I substitute in -2. Two to the -2 power is what? Oops. Isn't that what we're figuring out? What's 2 to the -2? Oh my gosh. Has everybody just drawn a blank on everything math related today?
Is it 1/4?
Mm-hmm. This is 1/2 squared, which is 1/4. Mm-hmm. What about 2 to the -1 power? What is that? Two to the -1/2. Mm-hmm. What about 2 to the 0 power? Christopher, you should know this now.
My bad, miss. I was doing something. Oh, what were we doing?
2 to the 0 power. What is 2 to the 0 power?
2, 1.
Yes, it is 1. Very good.
Okay.
Good. What about 2 to the 1st?
Would it be 2,
And 2 to the 2nd?
4?
Okay, very good. All right, I'm going to plot this exponential function. Here I go. So I know it passes through that, and we should know that because A is 1. And then I have, when it's 1, it's up at 2. When 2, it's up at 4. -1, I'm at a half. -2, I'm at a fourth. So here's my exponential growth function. This is y equal 2 to the x. If I reflect that, if I take its inverse, that's y equal x, I get a logarithmic function. Okay, and that's how we're going to write it. We can talk about how to represent those if you want. And we should, but we're running out of time. This is what's making me a little nervous. Now, knowing the relationship between a function and its inverse, I already know that I could interchange my domain and my range values because they're inverses of each other. So I could take this and I could say, all right, my y values are -2, -1, 0, 1, 2, when x is 1/4, 1/2, 1, 2, and 4. All I've done is interchange my domain and range values. Now, if I were to plot those points, at 1/4, I'm at -2. At 1/2, I'm at -1. At 1, I'm 0, 2, 1, 4, 2. So this is y equals log base 2 of x. Hopefully you notice that this base here, and again, I'm kind of skimming over this a little bit, is this base here. So these are the graphs of the two functions. Now, if I look at this parent logarithmic function, that's my parent. If I look at this parent, out of curiosity, dare I ask if the base of the logarithm isn't represented? Do you know what it is? This will tell me a lot whether you know logarithms or not. If you don't see a base there, like the base here is 2. If you don't see a base there, do you know what that base is? From Algebra 2, do you remember?
Just 1.
I'm sorry?
Is it just 1?
No, it is not. Does anybody else think they remember from Algebra 2 what the base is if we don't see it? Anybody? Oh my God.
0.
No, it's breaking my heart. Y'all don't know this from Algebra 2. Would it help if I said that this is also known as a common log if the base isn't written?
10.
Nathan, thank you. If the base is not there, the base is 10. There's also something known as a natural log where the base is e. And that's represented instead of log base e, it's just ln. Okay, I would love to spend time on this, but for me to be able to get to one more topic that I want to cover before we finish our time together, I'm going to have to skip this. So, oh, you're killing me. All right, that's okay. That's okay. It's not okay, but we'll do. All right, so here's our parent, log of x. What I want to focus on here is what do these transformations, because I told you these transformations apply to every function, so it applies to logarithmic functions. Can you describe the transformations made to this parent here? What am I doing to this graph here to get this? How would you describe that? What happens when we subtract 1 from x? What does that do? What transformation is that?
Horizontal shift to right.
Thank you. It is a shift right. So if anything, your takeaway from this class is that we know transformations and parent functions and domain and range and inverse. So this is a shift right one. So then we would just do this, right? Now, what if I look at this? What transformation is represented there to the parent?
Vertical shift down.
Yes, it is a shift down. So that means I would take this parent and I would just move each of these points down 1. Now, I will tell you, in a nutshell, I would have done a discovery with this, but understanding the relationship between the shifts and the transformations made in a logarithmic function compared to if you were to reflect it, they're opposite. So if you do vertical shifts in a logarithmic function, they become horizontal shifts in its inverse, the exponential. Similarly, if you do a vertical shift in the exponential, it becomes a horizontal shift in the logarithmic. Do you want, I'm going to give you the option here. Do you want to do more on logarithmic functions, or do we want to move on to polynomial functions? If you want to spend more time on logarithms, that was something in Algebra 2 that really caused you grief. If you want to spend more time on logarithms, I can spend the remainder of today's class on logarithms. Raise your hand in teams if you want a little bit more on logarithms, like how to convert from exponential to logarithmic and simplifying. Eric says more on logarithms. Anybody else want more on logarithms? Raise your hand in teams. Abiella wants more on logarithms. Nathan. Okay. Majority rules, we're doing more on logarithms. Okay. Good, because they're not hard. They just, everybody, that is the test that people do the worst on in Algebra 2, because it's, until you see it, it is a disaster. But once you see it, it is beautiful. Okay. Now let's do this super fun puzzle. You have this in your packet. What I want you to do with this super fun puzzle is I want you to look at each of these. I've just given you some information. And what I want, I've told you that this is a fact. This is true. What I want you to figure out is a pattern, looking at those numbers, kind of, Nathan, how you did with the circles and the triangles. Can you see a relationship among those 3 numbers? Can we write an equation that allows us to relate those 3 numbers? Try to find a pattern, and then when you think you have a pattern, see if you can answer any of the ones down below using the pattern that you have discovered. When you think you have it, let me know. If you think you have the pattern, let me know. And then tell me what any of the ones down below should fill in the blank. Take a moment and see if you can look and recognize a pattern. If you think you have figured out the pattern from the 3 examples given, tell me what the answers should be down below. If you think you got it, tell me one of the answers. And you can tell me whichever one. You don't have to go in order. When you think you have it, tell me any one of the blanks down below. Take a moment to try to figure out a relationship among the information that I've given you here and apply that down below. Eric, you think you got one? Give me one of the answers down below. Which one do you want to give me?
Number 1.
Number 1? What is number 1?
I got 4.
That is correct. Okay, so now y'all have another piece of information to add to the facts that have been given. When someone else thinks they have another one, tell me what it would be. Any one, if you think you've got any one of the ones down below. Christopher, which one you want to give me?
Number 2.
Okay, what's number 2?
6 or 2.
2, you are correct. That is correct. Okay, so Christopher's given us another piece of information to apply. So we have now 5 examples. Does anybody else have an idea of another one to fill in? Do you see the pattern? Christopher has another one. Give it to me. What you gonna give me? Which one?
Number 3.
Number 3. Okay, what'd you get for number 3?
15.
I don't get 15.
No? Okay.
Keep trying, Christopher. I know what you're doing, but you're almost there. Eric, you got another one?
Yes, number 3 is 125.
Yeah, I agree with you. It is 125. Okay, y'all, are we seeing the pattern? Anybody else have any other ones they can fill in? Natalie, Nathan, Abiella, Ariana. Nathan, Natalie, Abiella, Ariana. Okay, I'm going to give you a second. I'm going to let you figure out the pattern. If you need to use the facilities, by all means, you can use the facilities now. I want to go over these and discuss the pattern and how this applies to logarithms. So try to figure out the rule, the pattern from these examples and answer the last ones. Christopher, you want to give me another one?
Is 4 -2?
Nope. Close. Nope.
Is 7 3?
Well, 7 is 3 because I gave you that one. Nice going, Nathan. Give me another one. Give me another one, Nathan.
My bad.
No, if you didn't look at that example, then yay. If you looked at that example and just took it, give me another one. Natalie, do you have one for me?
Is number 6 9?
Yes, number 6 is 9. I think you have a pattern, huh? Christopher, you give me something else? What you got?
Is 4 1?
Nope. Third time's a charm. Think about it. Give it to me again. Natalie, you got another one?
Oh no, I accidentally kept my hand raised. But would number 4 be -2?
No. Keep going. Keep going. Eric, you got another one?
Would number 5 be -3?
Yes, number 5 is -3. Look at all these examples you have to figure out the pattern. That number 4, it's gonna kill you, huh? Number 4 is gonna kill you. No. Anybody got number 4?
I think I know it, but I don't want to ruin it.
You think you know it, but you don't want to tell me. Christopher, you think you know it? Third time as a charm?
Is it 2?
No.
Oh,
Eric, do you have it? Or Christopher, you want to try again? Come on, Eric.
I think it's 1/2.
I think I would agree with you. There we go. All right, now that we've done these, can we go back to the original ones and describe the relationship? How are we using, ignore that word power. What is the relationship? How could I rewrite these numbers? What was the pattern? How are the 2, the 3, and the 8 related? Y'all saw the pattern. You should tell me.
So power is a value that's being multiplied, and the number 3 is the amount of times it's being multiplied.
Okay, so there's my base. There's my power. Is that what you mean? Because 3 is the times you're multiplying the 2.
Yes, ma'am.
Okay.
That way you're wrong.
That's all right. That's all right. You had the right idea. So how would we write this as an exponential? I mean, this is an exponential equation. How would I rewrite this as an exponential equation for this example? Based on what you just said, how would I rewrite that? What to what power equals what number? Christopher, you want to tell me?
3 to the 4th power?
No, equals 81. So that means 16 to the 3/2 power is 64. Now, if I wanted to rewrite that rational exponent, I could say the square root of 16, the square root of 16 cubed, right? Which is 4 cubed, which is 64. So that means 2 to the 4th equals 16. 6 squared is 36. 5 cubed is 125. 2 to the -1 is 1/2. 10 to the -3 can be represented as 1 over 10 cubed, which is 1 over 1,000. 9 squared is 81. And then, as we said before, 3 to the 4th equals 81. So this is the relationship. Well, guess what? This notation here, where we wrote power, number, well, actually, yeah. What do I call this? Let me just call this C. And then let's call this A. Doesn't really matter. This little notation here, power, with this little subscript, which is a base. This is your argument, your input. This is your output, your answer. This is the same exact notation as that. So this, instead of the word power, that is a log. That's it. That's where it comes from. Logarithms relate to exponents. So the output to a logarithmic expression, this is an exponent. This is an exponent. The output to a logarithmic equation is an exponent. So if I change all of these to log base 2 of 16 is 4, log base 6 of 36 equals 2. Log. Do you see how I'm just rewriting the word power with log? And do you see how each of these become the exponent? This is a demonstration of how to convert from logarithmic form. Oops. This is logarithmic form to exponential form. And the relationship is that they are inverses of each other. So logarithms are exponents. They're just represented in inverse notation. So I like to do this little puzzle because if you start throwing in logs in, people start freaking out. But if you see the word power, the power of the base 2 to get 8 is 3. The power of base 2 to get 1/2 is -1. Power is exponent. The exponent for base 9 to get 81 is 2. The exponent of base 3 to get 81 is 4. That's all you're doing. Now that we've done, it's cool, super. Let's go over logarithms. Let's talk a little bit more about logarithms. So a logarithm just means an exponent. The output to a logarithmic expression is an exponent. So we talked about how to go from logarithmic form to exponential form. This is logarithmic form, where the output is the exponent. This little number down here is known as the base of the logarithm. And then this is known as the argument, which I didn't define here, but I can. And you can put parentheses there. That's your argument. The argument is also known as the input, the domain. To convert that, we take the base, this little subscript, that becomes the base in exponential form. The output is the exponent. The argument is x. So this is how you convert from exponential form to logarithmic form and from logarithmic form to exponential form. The base of the logarithm becomes the base in the exponential form. The input, the argument to the logarithm, is your output. The result of the logarithm is your exponent. So you should be able to convert from logarithmic to exponential easily. Let's try a few examples. Here you have been given the exponential form. You are being asked to convert it to logarithmic form. So how would I rewrite this? This would be log base what? What is the base?
2.
Yes. This is log base 2. That's a subscript. It comes from here. Of what?
32.
32 equals the exponent, which we said was 5. So try to do the next 3. Try to convert this one to logarithmic and try to convert these to exponential. I'm going to run to the restroom real quick while you do those 3, and we will go over those 3. Did y'all get it? Log, what is the base?
5.
5.
Excellent. Of? What's the input?
1 over 125.
Beautiful. 1 over 125. That's hideous. Let me fix that. And that equals?
-3.
Excellent. Now, can we go the other way? What would the base be? In exponential form. So here I have logarithmic form. I want to convert it to exponential form. What would the base be?
4.
4.
Excellent. 4 to what power?
2.
Excellent. Equals?
16.
Beautiful. 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 What about the next one? Ooh, I don't see a base. What did we say the base was if we don't see it?
10.
10.
10. Good. So that'd be 10 to what power?
-2.
Beautiful. Equals 1 over 100. And that makes sense because 10 to the -2 is 1 over 10 squared, which is 1 over 100. So you should be able to convert from exponential to logarithmic. We're just interchanging the x and the y. That's really what we're doing, but we have to understand that they are inverses of each other. I personally think it's easier to go from logarithmic to exponential. I mean, for me, that's easier. I can see that little base of the logarithm, and boom, it's done. Okay, any questions on that? Okay, what if I ask you to evaluate these? There are some rules for exponents, and I don't know if you know the rules for exponents. Well, I could just set these equal to x, and I could solve. I could simplify that way. If I set this equal to x and say, what does this equal? I could easily convert these to exponential equations and find x. So go ahead and evaluate each of these logarithms. Tell me what you get. So evaluate each of these. The easiest way to do it, in my opinion, is to go ahead and convert them to exponential equations. Let's simplify each of those and see what we get. So in other words, I could rewrite this as 2 to the x equals 16 and then ask myself 2 to what power is 16. So that's one way we could do that. When you think you have all four, raise your hand in teams. We're technically just setting each of these, if you wanted to think of it this way, equal to x, and then rewriting it in exponential form. Or if you want to put little question marks here, you can put little question marks here. Okay, Nathan thinks he has all 4. When you think you've evaluated all 4, let me know. So in other words, this would be 7 to what power equals 1 over 49. This would be 25 to what power? Equals 5. And this would be 2 to what power equals the 5th root of 2. When you think you've figured out what each of these simplifies to, raise your hand in teams. Nathan has his hand up. Does anybody else? Eric, Abiella, Christopher, Natalie, Ariana, any ideas? Do we know what the first one is? Nathan, tell me what the first one is.
4.
You are correct, right? So 2 to the 4th is 16. So this simplifies to 4. Raise your hand when you think you've got them or you're ready to go over them. Raise your hand when you think you've got it or you're ready to go over it. Okay, Christopher thinks he has them all. Okay, Christopher, what do you think the next one is?
I think the next one is 1 over 7.
1 over what? What are we, 7 to what power is negative 1 over 49? What did you say?
Like the fraction 1
What's the exponent?
exponent?
What's the answer here? What's the exponent that goes here?
1 over 7, is that how you say it? The fraction?
7 to what power gives me negative 1 over 49?
Oh, 7 to the 1 over 7, I think that's the same.
No.
No, that's not it.
No, because if this were 1 over 7, then that would be the 7th root of 7, which is not negative 1 over 49.
Oh, okay.
Keep going.
I got -2 for that one.
And I would agree with you. Christopher, do you see why it's -2? 7 to the -2 power is 1 over 7 squared. Is that a negative 1 over 49? That's a positive 1 over 49. Why does that look like a negative? Crazy.
Yeah, I get it now.
Yeah. Okay, you see that? So that's 1 over 49. Does anybody think they have the next one? 25 to what power is 5? When you think you have it, let me know. What are we doing to 25?
Is
Huh?
the power 1/2?
Yes, because if you raise something to the 1/2 power, that's taking the square root. Excellent, excellent, excellent. Right? 25 to the 1/2 power is the square root of 25, which is 5. Now, what about the next one? I would convert that to a base to a rational exponent. Do you know how to rewrite that without a radical symbol? What would that be? 2 to what power is the 5th root of 2? What would the exponent be?
5.
Not 5. Close. It has a 5 in it. 2 to
1/5.
Yes. That is absolutely correct. Right? So to rewrite this radical expression with a rational exponent, you keep the base, and then this root index becomes the base of your rational exponent. So that ought to make it really easy to be able to answer the last one. What is the last one?
The power is 1/5.
Yes, that is correct. So you should be able to evaluate logarithms, if anything, by setting it equal to x and looking at the relationship among those numbers. Okay, so that's one way to evaluate logarithms. One way to evaluate logarithms. Now, there's more to logarithms than that. So let's go ahead and look at a few properties. So if I were to express this is an exponential equations. If I wanted to take this exponential form and represent it in logarithmic form, it would be log base what? B of B equals 1. Do you see how I've taken this exponential form and rewritten it in logarithmic form? That's the first step. If you don't see that, then we can't go forward. Does everybody see that? The base is this base. The output becomes the input. The exponent is the result here. So I've converted from exponential form to logarithmic form. This is telling us something very special. This is telling you that if you have the base of the logarithm being, I want this a different color. The base, Golly, this is going to kill me. There. No. Why is this doing this to me? There. Whatever. If those two numbers are the same, if the base of the logarithm is equal to the base of the argument, the answer is technically this exponent here, which is 1. We don't see it, but we know it's there. So if I were to give you log base 3 of 3, what would that equal?
1.
1. Okay, because technically the exponent here is 1. What if I were to give you log base 9 of 9 squared? What would that equal?
Two.
2. And what if I were to give you log base pi of pi to the 4th? What would that equal?
4.
4. Exactly. If the base of the argument equals the base of the logarithm, the answer is just the exponent. So that's a key to be able to rewrite those logarithms in terms of the same base to a power. Similarly, if I take this exponential form and I try to rewrite it in logarithmic form, it would be log base what? What would it be? What's the base here? That becomes the base of the logarithm.
B.
B. Okay. What's the input, the argument?
1.
1. And what's the exponent, the output?
0.
0. So what this is telling you is that it doesn't matter what the base is. It does not matter what the base is. If the input is 1, the output is always 0. Why is that? That is because if we go back to our exponential, the input being 1, right? For an exponential function, it doesn't matter what the base is. It will always pass through this point 0, 1, which means its inverse parent logarithmic function will always pass through x equal 1 with an output of 0. So if that is the case, it doesn't matter what your base is. It doesn't matter what your base is. If the input is 1, the output is 0. So y equal log base, it doesn't matter. And why is this not showing up? There we go. It doesn't matter what this b is. If the input is 1, the output is 0. Because we always, the parent logarithmic function, unless I've transformed it and shifted it different directions, will always pass through the point 1, 0. So if I give you log base 5 of 1, what does that equal?
Zero.
0, because 5 to the 0 power is 1. If I give you log base pi of 1, what does that equal?
0.
0, because pi to the 0 is 1. Right? Any number other than 0 to the 0 power is 1. The key is this can never be negative because based on the logarithmic function, we have a vertical asymptote, so it can never go on the other side of the y-axis. So that input, for it to be defined, has to be greater than 0. When it's 1, the output is 0. So those are two big things to know because they make evaluating logarithmic expressions much easier. Now, as I mentioned earlier and was curious if you knew, if you don't see a logarithm with a base, If the base is not initially represented, explicitly represented, it is a base 10. So that is base 10. So log x means log base 10 of x. I don't need to see the base there. Why is that? Well, because we live in the world of base 10, right? If you think of decimal values, right? This is the ones, this is the tenths, this is the hundredths, right? We live in the world of base 10. So that's why it's called a common log, because we exist in this world with base 10. Okay? So let's look at common logs. I could rewrite this as just this. I don't need to see that base 10. It exists. I don't need to see it. This is a common log. The reason you might want to see it is because if you know that it's there, you might want to rewrite your logarithmic expression where the base of the argument, is the same as the base of your logarithm. Okay, so that's why you'd want to go maybe from here to this form. Because can I rewrite 100 as 10 to some power? Yes. What would it be? 100 is 10 to what power?
Second power.
Second power. So if I can rewrite this argument with the same base as the logarithm, I can simplify that easily to what? What would this simplify to? Using this up here. What would that equal? If the base of the logarithm is equal to the base of the argument, this simplifies to what? If the base of the logarithm, yes, it just simplifies to the exponent. That's why you would want to maybe rewrite these with the same base. Okay, what would the next one simplify to? If I look at this, what does that simplify to? It's the same rule here.
It'd just be one, wouldn't it?
It would just be one, yeah, because the exponent here is 1, right? What about the next one? What would the next one simplify to?
0.
Yes, because the input is 1. What would the next one simplify to?
5.
5. Now, the next one you can't do without a calculator. You can't do that one without a calculator. I can't rewrite 90 as 10 to some power, can I? No. But you have, oh heavens. I can't open up my TI. Okay. On the calculator, there is a log button. The log button is right here. So if you type in log, and then put in the argument, in this case, it would be 90. Do you see that? Can you see that? It would tell you what that value is. So there is a common log button on the calculator. You can even graph common logs. So if I were to graph that, well, my window's horrible. Let me change my window. That's a terrible window. Oh, well, I'm not going to give you this. There's a log button on the calculator. Now, do you think, so this would be a decimal approximation. So do you think you could maybe guess and think about what that one would be? Notice here, and this is a little foreshadowing, we have the base here raised to a logarithm of the same base. Does anyone think that what that might equal? Can you be clever and maybe conjecture what that would equal? We said that the log that has the base equal to the base of the argument, is just the exponent. So what happens if I have a base raised to a logarithm with the same base? What do you think that would be?
90?
Yes, it would. That's another rule. So if these two are the same, the answer is just the exponent. If these two are the same, the answer is just the argument. Yeah, it's another trick. Now, we said a common log is log base 10. There is another log that is very popular, especially when you're doing finance or when you're doing biological modeling, and this one is known as a natural log. A natural log is based on that number e that I mentioned to you that Euler came up with. So instead of writing log base e, you can write ln. Log base e is the same thing as ln. Where does that come from? Log naturel. Ln means you're dealing with log base e. So most of the time, you will not see log base e. You will see ln, and you need to know that it's log base e. Why? Because if you're given something that looks like this, I could have given it to you as this. You would have to know that ln is the same thing as log base e. Why? Because then we could simplify to what? Easily. There's no work to be done on this one. What does this equal? Using the rule from the top of the page, what does that equal?
1.
1. Now, this is the same thing as ln of 90, and guess what? Right above the log button on your right below the log button on your calculator is the natural log button. So the calculator can do common logs and natural logs easily with these two buttons. You just put them in and then input the argument. Okay? So if you know these rules, it's very easy to simplify logarithmic expressions. Now, there are also rules of exponents that will allow you to expand and condense into single logarithms or more easily evaluate logarithms. I'm not going to get into those in the interest of time. But if you want to know more about rules of logarithms, quotient of like bases, and how that applies to the sum of logarithms with like bases, I do have those videos on YouTube, and you're welcome to watch those. Okay? So hopefully that kind of cleared a little bit more with logarithms up. Now I'm going to skip rational functions because it is a huge topic with holes and other discontinuities, but unfortunately we don't have time to discuss that since tomorrow is our last day, and there's other things that I think we need to have at our fingertips before we go into pre-cal. So pre-calculus talks about a very important topic known as limits. and then talks about whether things converge or diverge and what they converge to and what the limits are. And what this has to do with is what's known as in behavior. What happens, for example, at the endpoints, or not endpoints, in the far tails of a graph. So in other words, if I were to give you a graph, right, and let's say I give you y equals x squared, if I want to look at the what's known as the in behavior, I'm looking at what happens when I go to positive infinity and what happens when the graph goes to negative infinity. So that's going to be very important in pre-cal. So I want to kind of go and review a little bit with polynomials and in behavior, the tails, because I think that will help you a lot in pre-cal. So let's move on to polynomial functions. So if I am talking about polynomial functions, we've seen some polynomial functions. The polynomial functions that we've worked with are, well, quadratic functions are polynomial functions. Cubic functions are polynomial functions. Quartic functions are polynomial functions. In essence, x to any positive real number exponent greater than 1 is a polynomial function. So let's look a little bit more into polynomial functions, and let me pull something up ever so quickly so that you can see it. Because we're going to talk a little bit more about graphing those as well. So let's see. Okay. What do I want to do? Let's just revisit. You should be familiar with this notation. It may be a little confusing at first, but it's really not difficult to understand. So let's define what a polynomial function is first. A polynomial function in a single variable. And when you get into calculus, you can have functions. Well, actually, you can see that in pre-cal as well. You see functions that are of more than one variable. So right now, when we've looked at linear functions, we had the function of x. So I could write this as f of x equals ax plus b. If I had a quadratic function, I can write the function of one variable x as ax squared plus bx plus c. And if I continued to increase the power of x, I'm just looking at the decreasing value powers of x each time. So that's x to the first, and that's x to the 0. This is technically x to the 0, x to the first. This is technically x to the 0. So we've seen these before. These are all power functions. So if I'm looking at these power functions, I'm just looking at different powers of x. So this is the general form for a polynomial function. What this notation means is that I have coefficients. These are just constants. These are just real numbers. And this first leading coefficient cannot be 0. That's what those little a's are. They're just coefficients. And then I have these powers of x in decreasing order. And what those little n's are, they're just whole numbers. So these are examples of polynomial functions. Here are my coefficients. Doesn't matter whether I write A, B, or C, or whether I write A with little subscripts. If you notice, those little subscripts correspond to the power of x. That's just a way in general form to say, which coefficient am I? I'm the coefficient a for the x to the n power. I'm the coefficient a for the x squared term. So that's all this notation means. The degree of the polynomial is the highest exponent of x. So the degree here for linear would be 1. The degree here for a quadratic would be 2. The degree here for a cubic would be 3. Again, the leading coefficient is the coefficient for the highest exponent of x. Okay, now there's some terms that we use when we talk about polynomials. These are math terms. Smooth, the term smooth talks about whether there are any, well, this is a polynomial function is said to be smooth if it has rounded curves. In other words, there are no sharp corners. So example of smooth, well, I can have my parent cubic. I can have my parent quadratic. Things that are not smooth would be like the absolute value function or piecewise functions that look, have sharp corners. So these are not smooth. These are smooth, rounded, curved, no sharp corners. Another math term is the term continuous. And we've talked about this. We said a polynomial function is continuous if there are no breaks. In other words, I can draw the entire graph without raising my pencil. So I can draw graph without lifting my pencil. So examples of continuous function, again, that's continuous. That's continuous. Things that are not continuous, right? I would have to lift my pencil to draw that. Or I would have to lift my pencil to draw that. So piecewise functions are not always continuous. They can be. Well, they're piecewise continuous. This is continuous. This is continuous. So each of these pieces is continuous, but the entire graph is not continuous, right? Any questions on smooth and continuous? No? Okay. So then let's move into the discussion about the end behavior. Are we okay? Do I need to go back? Are we good? Speak now. I know I'm going kind of fast, but this is super. Absolutely. And I know I'm skipping some stuff, so, I apologize, but I'm trying to hit some key things that are really going to serve you well for pre-cal. So smooth means rounded edges. Continuous, I can draw the entire graph from start to finish without raising my pencil. These are piecewise continuous, but the entire graph is not continuous. Each of these pieces is continuous. The entire graph is not continuous. Now in calculus, they will say you have a continuous function, and that's going to tell you a lot about the function in terms of what you will evaluate. And I can't really go into detail about that because you don't know what you'll be doing with these functions. Okay. We're good, Abiela?
Yes, we're good.
Okay. All right. So the next thing I want to look at is what's known as the end behavior. What is happening in the tails? The tails of a polynomial function. So the end behavior, to identify what the graph is going to look like, I'm going to investigate what's happening with the leading term. In particular, the leading coefficient. that is going to tell me a lot about the tails, the end behavior. And again, the tails, the end behavior is what's happening as I go to positive infinity in the graph and what's happening as I go to negative infinity in the graph. Not what's happening in the middle, but what do the ends, the tails of the graph do? That is important. So here we have the general form. If I look at the leading coefficient, the leading term, the leading coefficient, if the leading coefficient is positive, that tells me, this leading coefficient tells me what the right tail does. If the leading coefficient is positive, the right tail is going to go up. If the leading coefficient is negative, it tells me that my right tail goes down. So the leading coefficient tells you about the right tail. For example, y equals x squared. What is the leading coefficient? If I don't see it, what is that little leading coefficient in front of x squared? Anybody? What is the leading coefficient to x squared? What is
2.
What is it?
2.
That's the degree. The degree is 2. It is a quadratic equation, but what is the leading coefficient? What is a sub 2, so to speak? What is the leading coefficient here? I don't see it. What is it?
1.
1. 1 is positive, right? So what can you tell me about the right tail for the graph? Since A is positive, what should the right tail do?
Go up.
It should go up, right? Well, isn't this just the parent quadratic equation? Yeah. Now, if I give you the equation y equals negative x squared, for starters, you should recognize that this minus sign is what type of transformation? If I take the parent function y equals x squared, by putting the minus sign out in front, what transformation are you performing on the parent function? What is that?
A reflection across the x-axis.
A reflection across the x-axis. So we know that this quadratic function's graph is going to open down. And that makes sense, right? Because the right tail should go down if this is a negative number. Does that make sense? So if I give you y equals x cubed, the parent cubic function, we already know what that looks like. And since the leading coefficient is 1, it makes sense that that right tail goes up. Okay? So the leading coefficient of a polynomial function tells you about the right tail. It tells you about the right tail. It tells you about the right tail. How do I know what the left tail does? The left tail has to do with the degree of the polynomial. So if the degree is even, the left tail does the same thing as the right tail. Has same end behavior as the right tail. It does what the right tail does. If the degree is odd, oops. If the degree is odd, the left tail, so it tells you about the left tail. If the degree is odd, it tells you that the left tail goes in the opposite direction as the right tail. So n is even, same in behavior. Odd, opposite in behavior. So that means for even, they either both go up or they both go down. For odd, if one goes up, the other goes down. Does that make sense? Yeah? So, determining what the graph looks like on standardized tests, on the SAT, on the ACT, if they give you polynomial functions and they give you graphs and say, which is the following, all you have to do is look at the leading term. You can narrow it down because if you know if the leading term is positive, that the right tail goes up, and if the degree is even, the left tail does the same thing. Okay? So, what I want to do in the last few minutes is I just want to look at in behavior. Now, the degree of the polynomial tells you how many roots you have. So the degree, and this got messed up a little bit. I don't know if yours is messed up. The degree of the polynomial tells you the number of roots. So an nth degree polynomial has n roots. Now they may be distinct, unique roots, or they could be repeated roots with higher multiplicity. So for a linear function, the degree was 1, you knew that it had only one root, potentially. It has no roots if it's a horizontal line that doesn't pass through the x-axis, right? Quadratic, n equals 2. So we would have 2 roots. Now, they could be a repeated root. They could be 2 unique roots, or you could have imaginary roots, right? Cubic, n equals 3, 3 roots. So let's look at this example. We'll end with this example because I know this is a little overwhelming right now. We'll end with this example here. What is the degree of this polynomial? The degree. What does n equal? What is the degree? I'm sorry? 4. The degree is 4. This is your degree. That is your degree. So that is telling you you're going to have 4 roots, right? The degree tells you the number of roots. Now, since the degree is 4, I know that this is a quartic polynomial, a degree 4 polynomial. But how many terms does it have? How many terms in this polynomial? How many things connected by addition and subtraction?
2.
2. So this would be classified as a quartic binomial. So I could have a cubic trinomial. I could have a quadratic monomial, depending on the number of terms. You classify based on the degree and the number of terms. Now, what is the leading coefficient of this polynomial? And again, you always want to write it in standard form, exponentially descending order, to identify the leading coefficient in the degree. What is the leading coefficient of this polynomial?
Two.
Not 2.
-2.
-2. It's the whole thing. Abiella, do you see that? You have to take the negative with it. Okay, so it's degree 4. The leading coefficient is 2. You have enough information to tell me what the tails do, to describe what is known as the end behavior. So let's talk about the end behavior. What does the right tail do, and how do you know? What does the right tail do? As I go to positive infinity, what does the right tail do?
It goes down.
It goes down. Yes. It goes down because the leading coefficient is negative. Do you see that? My right tail is going to go down. Now, is the left tail going to do the same thing, go down, or is it going to go in the opposite direction? And how do you know?
It's gonna go up
Why do you say that?
because it's plus 2x.
This doesn't matter,
Oh, never mind.
right? The only thing that we look at to determine the end behavior of the tails is the leading coefficient tells us the right tail. The degree tells us whether the left tail does the same thing or goes in the opposite direction.
It's going to do the same because it's even.
That's right. Even degree tells us it does the same thing as the right tail. The right tail goes down because the leading coefficient is negative. Good job. Now, I'm going to stop there because that's a little heavy duty. Well, let me give you one more. Why not? Just give you one more. What is the degree?
Three.
3.
3. That implies that I have 3 roots. Okay. What is the leading coefficient?
5.
5. Excellent. Okay. How many terms do I have?
3.
3. Okay. So since it's degree 3 and I have 3 terms, how would I classify this? Well, how would I describe it? Since the degree 3, we would call it what type of polynomial? Degree 3. Degree 1 is linear, degree 2 is quadratic, degree 3 is
Cubic?
yes. Beautiful. Beautiful, Natalie. And since it has 3 terms, what do we call a polynomial with 3 terms?
Trinomial?
Yes, it is. Natalie, you're on a roll. So that's its classification. So now tell me about the tails. The right tail does what?
It goes up
And how do you know?
because it's a positive.
The leading coefficient is positive. Yes. And what does the left tail do?
The opposite because it's odd.
Yes. Do y'all see that? Okay. So tomorrow we will talk about how to find the roots and to graph it a little bit better. Just maybe a couple of examples for those. Then I would like to look at something called arrow notation because that is huge for pre-cal. So I have to do that with you tomorrow. And then we'll do a tiny, kind of like we did the mid program last Friday evaluation. I'll do one more tiny one like that for feedback and just some quotes from you. And then that will be it. So y'all did a great job. I think you're you did a lot today. So I'm just gonna leave you unless you want puzzle. You want puzzle? Or you exhausted? You exhausted. Okay, fair enough. Fair enough. Fair enough. Y'all have a wonderful rest of your day, and I'll see you for our last class tomorrow.
Bye, miss.
Bye. Good job.
I missed the day.
Bye.